Welcome to our YouTube channel. We're going to be covering teaching fuel trim, but this fuel trim techniques that we're going to be teaching can be used for the technicians out in the field. So let's get started in the class. When you're teaching fuel trim, you're going to need some objectives when you're teaching it. One of the first things you're going to have to cover, what is fuel trim for your students? How do we need to test it? And we have to do, what are good readings, what are bad readings? How do you diagnose what is good, what's bad? And do you need a road test? A lot of times we find out that the fuel trims will not set exactly with a problem in the bay, so we have to do a road test. So that's what we're going to cover. And we're going to start in teaching you what is fuel trim. Fuel trims is a trend based off information from the sensors that we've got. It's a correction based off of the O2 sensor. We have a course adjustment that comes from the sensor when we first fire it up, but once we get the car into closed loop, we're using the O2 sensor and we're going to get what we call short-term fuel trim, which is the information coming across exactly from the O2 sensor as changes in the vehicle. So if we're looking at vehicles and we're looking at the data, the older OBDII data is slower than the CAN-equipped vehicles. CAN came out in 2008. Anything 2008 and later is going to have faster information. And if we're looking at the OEM or enhanced side, domestic vehicles, we're looking at the information. There's 4 possible ways it's going to display it. Now the first one is short-term fuel trim or adaptive short-term fuel trim. And the reason that we're looking at adaptive, the European cars will use that, but so does Chrysler. They use ADAPT as far as you're looking at information short-term fuel trim. Short-term fuel trim is based off a correction, a temporary correction based off O2 sensor input. So if the O2 sensor goes high, you're going to see the short-term correct that information and go the other way, which we're going to show on a slide here. The other thing is that's always there. That's volatile information, which means when you shut the key off, it's gone. So if we have long-term fuel trim, or adaptive long-term fuel trim, what its job is to do is put a memory up there as a correction. Its correction is always to bring the short-term fuel trim back to home, what I call zero, plus or minus 0. If I'm on a Chrysler car, I erase all the data, it goes plus or minus 3%. I know that for a fact because I've tried this. So if we're looking at that as a correction, so long-term fuel trim, if the O2 sensor is staying high for a long period of time, so it's running rich, the computer is going to, with the long-term fuel trim, take fuel away. If it's running lean for a long period of time, it's going to add fuel. So we're going to look at corrections to bring the short-term fuel trim back to the center so we have fuel correction based off of the O2 sensor. Now there's another thing called total fuel trim. Total fuel trim is where a lot of technicians and a lot of instructors will add the long-term fuel trim and short-term fuel trim together. When they do that, they do it, I like doing it a little bit differently. What I like doing is adding the average two together they really get, because the short-term fuel trim is constantly changing. So I get the average of what it should be. And they're doing that as a possibility. On some General Motors cars, you're going to see a total fuel trim based off of different information, or a Toyota, you're going to see it's based off an algorithm and using other sensor information and the rear O2 sensor to do what they call total fuel trim. So what we're going to do next is show you how this corrects back and forth using some data. Okay, we've got the fuel trim control we're looking at on bank 1. I did this just one bank so we can concentrate on what's going on with this. So I have the O2 sensor, I have adaptive fuel trim, so I know that when we're looking at this is a Chrysler vehicle, and I also have the injector pulse width. These are the 3 items that are working together to do fuel trim. Most of us out there look at fuel trim, but you don't realize we really need to look at the injector pulse width along with it. So I'm going to go ahead and play this. And if we look at the full screen up here, and I'm going to click it for a second. So if you look at the O2 sensor is at 0.76 up there, you will notice the short-term fuel trims, what is it doing? It's down below to compensate for that. It's going to be adjusting the pulse width to the injector. And in this one is in microseconds, so it'd be 1.72 fuel right at the moment. Now, this one doesn't do average, so we're just doing whatever it is right now. So we're looking at the data up here. It's constantly going back and forth. So I'm going to go ahead and allow this to go forward. and you're going to look at the corrections we're going to be live on your scan tool. Now, if I'm looking at data, again, when the O2 sensor goes up or down, we're going to see the opposite reaction with the short-term field trim. At the same time, we're going to see an injection correction to bring it there. So if I say these are trending together, whatever happens with one is going to have the opposite reaction with the other. And that's how you know you have field trim with short-term field trim doing its job on the vehicle. Right here we have an OBDII example, and what we're looking at, I've got my RPM on it. I have my long-term field trim, which you will see is at minus 2.344. If I blow this up a little bit, you can actually see the point that I'm looking at is minus 2.344. At the same time, I'm looking at my short-term field trim. It's constantly correcting. So notice something. Long-term field trim does not change if you're in a particular cell. It's not going to do anything unless you change RPM and you go to a different cell or different correction. So my short-term field trim is moving. If I go back over here and look at my information, I'm looking at my O2 sensor. Now this particular scan tool is telling me what it is right now is 0.68, but I've got a fairly good operation on my O2 sensor, giving me good information. And again, I'm at this RPM. Now, I also would tell you if you were checking this data up here in OBDII, I would actually go to about 2,000 RPM and hold it there, and you'll get a little better activity off the O2 sensor. But this is just showing you an example of what you might be doing for an example on OBDII and give you any information if everything's working right. But again, this is at a specific RPM, a specific load. So we have to talk about a couple of things as we go across in the next few slides of how the monitor actually runs. When we look at field trim monitor driving instructions, what you have to realize is not all the vehicles will have the same instructions. We're going to have some examples of that as we go across. One of the things that I've seen a lot of technicians do, they will run the car and then they'll shut the key off. Whenever you shut the key off, you have to start all over from the beginning. Now, readiness codes or readiness status, depending on how you want to word it, are cleared whenever the battery's disconnected or the ECM cleared with a scan tool. When that happens, you're going to see that the comprehensive component monitor test, you're going to look at the field trim test and the misfire test. Monitors will always say, for the vehicles I've looked at, will always say they have completed, even though they don't. It just means that's a default how the data is being delivered. So we have to have a dry cycle. Now, you also have to keep in mind when you're looking at field trim codes, it takes 2 trips for them to set. All right, so you think about this. You might have to drive the vehicle under readiness status and the information needs to be done. You might have to drive it 2 trips to make sure you don't have a failure. So we're going to look at the dry cycle to turn the readiness status to say the monitor has completed and it has run, and then after that, the light should stay off if we're looking at information. So the first one we're going to look at is a GM example. Now, we look at it, we've done some characters up there. Those look really nice, a lot better than the one I really had before. So I'm going to go up and blow this up and look at my driving instructions. So we have code criteria that comes up, how you have to run the monitor. That's code criteria, and a monitor code criteria. So it says we have to clear the codes. I'm not clearing codes unless I'm actually going out and the vehicle has been fixed, or I think has been fixed. So it says clear codes. I wouldn't recommend that, but a lot of guys go ahead and do that. It's up to you. I do that as my last step. So it says the ECT PID has to be minus 36 to 302 degrees Fahrenheit. 302 degrees Fahrenheit, I think that's a little too hot, so we have some process there. Inlet air temp, minus 4 to 302. And if we look at our barrel PID, has to be over 70 kilopascals. So we have for different altitudes, we have a different setting on this and our process. So if I'm over 70 kilopascals, that would mean I'm above about 5,000 feet. I think I might be wrong on that one, which means I'm not going to be able to run this monitor to completion. So around where I live, I'm going to be somewhere between about 90 kilopascals or whatever, or 28 inches of mercury. So I always flip it over to 28 inches of mercury and see the correlation there. So the next thing it tells us to do is drive this vehicle to 55 miles an hour. And when it says accelerate, that does not mean like most of us do with our foot flat down to the floor. That means accelerate like a normal person would do. And accelerate to 55 miles an hour. Then you're going to back to 25 miles an hour with a closed throttle. Now I'm looking at the closed throttle, that means what am I going to be doing with my gas pedal? I'm going to be off the gas pedal and let the vehicle decelerate on its own. So we look at, you have to repeat that step twice. And when we go to our next one, it says check the monitor status. It says that in the drive cycle, review the status of fuel system monitor on Scantel. That again is in mode 1, okay, as part of mode 1. Mode 1 is the readiness status plus data. So you have 2 points of mode 1 in your OBDII Scantel. So that gives you some information how you would run this on this General Motor product. And you might want to look up the drive cycle because some of them were different on some engines, even within the same manufacturer. Okay, I want to give you some instructions you might get with some different scan tools or some different OEMs, but I like using these as tech tips when you're doing this. So it says whenever a range is provided, try to operate in the middle of the range. Now, the last one we did, it says 55 miles an hour. It's what they're looking for, so you need to be in that range. If it tells you I need to be 45 to 65, we're going to probably set it as close to 55 miles an hour. If it says that the short-term fuel trim range is minus 20 to plus 20, I'm going to try to get my car operating as close as I can to be averaging 0%. This is what you're going to be looking at to try to get accurate information. If you're at one edge or the other edge of the spec, there's a chance you will go out of that. If you try to be in the center, there's more of a chance that you'll be able to complete the drive cycle. That's a tip to look at, and I've had trouble with this, especially on some European cars. The other thing you want to do is set your scan tool up. Do not give all the data on the scan tool. Pick the PIDs that are needed or the parameters that are needed specifically for what you're testing. So if I'm looking at a car and I want to look at short-term fuel trim or the load on the vehicle or the long-term fuel trim and the RPM and the vehicle speed, that's all I would set it up for. I'm not going to be setting up all the data because it slows the data down. You want to pick the parameters or the sensor data specifically for the test you're running, not everything else. It makes your data a little bit better. So there's some tips to running the fuel trim monitor that might be helpful to you as you go across. It will definitely has helped me in the past. Okay, we have a drive cycle for a Hyundai here. This happens to be a neighbor's car, an earlier Hyundai that had a problem. And first thing, it's going to come with a lot of the same information if you do the data. Not all of them are going to display this, but it's a good idea. Do not turn the ignition switch off. That's common. If you do that, we have to start over again. And again, it tells you that if we disconnect the battery, all the mode 6 data is erased, all the readiness data is erased, so we have to start there. Clear. If I clear DTCs with my scan tool, same thing. I'm going to lose all that information. Now, the drive cycle is used to determine if the readiness code for this monitor will complete. In other words, if we run the monitor for this particular test, it will be on. And we want to make sure that monitor stays off. There is a chance, the light stays off, excuse me. There is a chance we can complete a monitor and still have a code set, so keep that in mind. Now, if I go to my next slide here, we have the fuel system on it. Now, again, every car manufacturer are going to do this slightly different. Even though they're a universal one, I've learned that you want to do your research and find the proper drive cycle as we go through there. And when we go to my next slide, you're going to see some code criteria you might look at. So the first thing we want to do is clear the codes. They say that. Again, that's clearly up to you guys. I don't do that, clear codes. I want to run the monitor and see if the car tries to correct itself. So it says, first of all, bring the inlet air temp sensor and ECT PID up on your scan tool. The ECT must be above 140 and the IAT between 40 and 140 degrees. So basically they were telling you, I need to be in closed loop, all right? I need to be closed loop for this monitor run. Which fuel trim? That makes sense. The barrel has to be above 72. Notice General Motors says 70, they say 72. It's always going to be close to that in the range we're looking at it. The next thing it says drive between 40 and 55 miles an hour. So if I was doing that, that's a 15-mile-an-hour range, so I need to be somewhere about, if you divide it in half, that's 7.5, so I'm going to probably look at 48, 49, somewhere in there. I want to be in the middle so I do not fall out as I'm driving this vehicle. And you're probably going to be doing this on the highway or on a two-lane road somewhere or whatever. And then you want to do stop-and-go traffic. The reason they want you to do stop-and-go traffic is basically to relate to what's going on in different load conditions on the car. The next thing it says, repeat this step 2 more times. So when you run this, you're going to have to do it, complete it, and then you're going to turn around and have to do it again 2 more times. This is something you need to look at. At the end of the drive cycle, they want you to make sure the fuel system monitor on the scan tool. Again, that's part of mode 1. You're going to look at it and make sure it's completed. This is the way you're going to be running the information for this particular drive cycle. And again, always look up the information, how the drive cycle is run on the car you're working on. And not all engines have exactly the same drive cycle. Keep this in mind. And we're going to go over, I'm going to look at code criteria next. Okay, when we're looking at code criteria, there's sometimes when you're reading the information, you want to be very careful. So this one says, in order to provide the best results of the drivability, fuel economy, emission control, it uses closed loop for air metering. PCM monitors the O2 sensor voltage and adjusts the fuel delivery based on the closed loop fuel control, based off the O2 sensor. Change in fuel delivery indicated by long-term and short-term fuel trim values. Ideal fuel trim values are always going to be around 0. PCM will add fuel when the O2 sensor is indicating a lean condition. If it's a lean condition, it will be under 450 millivolts. Additional fuel is indicated by rich when they're above it. So if you're looking above 0, it says in here the PCM will reduce the HO2 signal is indicating a rich condition. If you saw that and didn't know anything about fuel trim, you might get a little confused on it. What it basically means is we are going to reduce the pulse width to the injectors to reduce the O2 sensor signal. Let's say it's averaging 450 millivolts, it's good. 600 millivolts would be indicating a rich condition. So what we're going to do is reduce that O2 sensor signal by reducing the pulse width, which is indicating a rich condition. And as just talking about it, we want everything to be as close to 0 as we can. Now, DTC description. If long-term fuel trim and short-term fuel trim are above the standard values, the PCM determines that a fault code is there and a DTC is stored. That takes 2 trips, again, to do this. Now, if we look at it, it says this. DTC strategy, fuel adaptation, are a value of the air-fuel feedback. And if you notice, it's got a little bit of question mark in there. So sometimes your OEM information is bad. Or not bad, but it's not always the best to read. It says we have to be in closed loop. Well, that's normal sense. It says threshold value. The air-fuel learning value is above 20%. That means the long term's above 20%. And the air-fuel feedback compensation, this is the way they read it different, is at 5%. So we're looking at air-fuel learning value. Learning value, that's the value that is learned to correct. That would be long term. And the feedback compensation would be immediate, would be short term, says above 5%. The next thing it says is the diagnosis time is going to be continuous. Once you get in closed loop, it's continuous. And I like this statement down there. The MIL condition will come on in 2 drive cycles. Now, if I go over to blows up and look at this other possibility here, if we go over here, that will give you possible causes. This is great. It says air leakage. That would be air leakage would be what we would call a vacuum leak. And we would see hoses, connection, intake manifold, whatever. Improper fuel line pressure. Now on this particular car, the fuel pressure regulator is regulated by vacuum off the engine. So that would be a possibility. With a broken hose would correct the fuel pressure. It's got a faulty injector, faulty fuel pump, or faulty PCM. So these are all possible things that could come up on this particular vehicle. So that is a code criteria. It is always a good idea to read it, but there are some times when they describe things, especially on some of the European and the Asian cars, it might not be exactly what you would expect. So you have to put a little bit of think when you go into this information. And let's go over to another thing. Okay, we're going to look at a TSB on this particular Hyundai that we were showing before. So I want to blow this thing up so we can look at it. First of all, this is an older TSB, but it's still pertinent for some diagnosis that you would do on a vehicle today. So it's got a 171 and 174, 2 lean, bank 1 and bank 2. Always keep in mind if both banks have the code, that means the problem is common to both banks, which could be a mass airflow sensor, fuel delivery on the vehicle, something else looking along those lines. So the first thing they want you to do on this particular vehicle is they want you to look at the mass airflow sensor at idle in 2,500 RPM. And what they want you to do is look at the long-term fuel trim. If they're above 10%, if the readings are both 10% or greater for long-term, not short-term, long-term, they want you to do this particular test. Now, this particular test says this. It says look at mass airflow sensor voltage reading. This is an analog mass airflow sensor, not a digital one. So key on, engine off, it's 1,000 millivolts, or what we would call 1 volt. It can be, you can have a change of minus, or plus 50 millivolts off that range. So I can be a little bit over there, but it's there. The next thing is they want you to check it at idle and park. So we want to go to 1,400. We want to go to 1,400 millivolts or 1.4 volts. So we get a change from key on, engine off, and a lot of cars don't have this reading, but this is similar to a Bosch analog sensor you might see on some of the cars for Europe, and the sensors ranges are pretty close. At idle and park, it should be 1,400 millivolts or 1.4 volts, plus or minus 50. 2,500, it should be 1.9 millivolts, 1.9 volts or 1,900 millivolts. And if you put a wide open throttle, it says driving while driving the vehicle, you could do it in the bay. I've done it in the bay many a time. You want to see 4 volts minimum. If I don't see 4 volts, I've got a problem with a mass airflow sensor. If it doesn't meet the criteria, they want you to replace the mass airflow sensor. But before you do that, they want you to do this, which is somewhere down the line that, hey, I got a mass airflow sensor code or this code, you replace it. But the thing about it is they want you to check to make sure you have 5 volts reference on the system. That's your input voltage. And you want to make sure that you have a proper ground. On this particular ground, this car had a ground issue, and it was like 0.1 volts. You want to be less than 50 millivolts on this particular vehicle. The next thing they want you to do, if the 5 volt reference is good and the ground's within specs, they want you to confirm fuel pressure between 35 and 39 at idle with the fuel pressure regulator hose connected. Remember, where there's a change, if I have the hose connected, we get vacuum from the engine, and it's going to keep this down here. And the next thing they want you to do is 44 to 48 psi with it disconnected, which would be when you do a wide open throttle, the pressure would increase because you're losing vacuum. If the 5 volt reference, ground, and fuel pressure within specs, they want you to replace the mass airflow sensor. So that's how you would do this. It's a neat little trick, and you can do this on a lot of sensors that have analog mass airflow sensors. Okay, the load on the vehicle matters. I've already talked about that again, but we're going to look at this information. So the first thing I want to look at is this was an inexpensive scan tool. I only set it up for engine speed, calculated load, short-term fuel trim, long-term fuel trim. It happened to be a 4-cylinder engine, so we know that is a fact. Now, if you look at the information, and if I go across and look at the information, I'm at 1,564 RPM, and on frame 2 on the left, and 4.4 on the right. So if you look at it, my engine speed is 1,564, and it's 1,568. So I'm within 4 RPM on this particular vehicle, really close. Now, the next thing I wanted to look at is calculated load. The calculated load is at 27.8 on the left, and we're doing a vehicle speed of 0. At 22 miles an hour, I got a calculated load of 54.5. Now I'm going to go back and look at my short-term fuel trim on the left-hand side. I'm at minus 5.5, so I'm in that 5 to 10 range, so that looks pretty good. But if I notice underneath there, I've got long-term fuel trim of 14.1, which means is somewhere down the line, I have added fuel to compensate for the short-term fuel trim. So it means is I've added fuel to compensate to get the short-term fuel trim back to where it should be, plus or minus, around the 0 point. So it's doing plus or minus 5.5. That means I'm in range less than 10. So it shows me I have a good correction on a particular vehicle to compensate for something going on. If I go to the vehicle going down the road at 22 miles an hour, my short-term fuel trim is 1.6 at this particular point, and my long-term fuel trim is minus 2.3. But they're both within 10% and they're real close to 0. So my problem on this particular vehicle is an idle problem, and I have learned a correction so the car runs fairly well, but I still need to address an issue where the car is running lean and it needs to be repaired. I have done long-term fuel trim to compensate for it, and if you see these kind of numbers, that usually means that we have some kind of fuel-related problem on the vehicle. So there's really a good idea to find out how to analyze what's going on. The car did correct it. I do have fuel trim there. I have fuel control in the vehicle, and it's a long-term correction for a problem that we had at idle. Fuel trim cells, those are the correction areas that are using for long-term fuel trim, and also short-term fuel trims there too. But the corrections are learned in a cell. GM and Chrysler supply them in the data stream. Most of the other car companies do not, but GM and Chrysler do. The other thing is, if you have the Ford OEM scan tool, and I think about 2013, 2014, you should be able to get that in the OEM tool. But I want to let you know that some systems have 2 cells, some of them have 96 cells. If you work on European cars, they will call it ranges, and some of them have 2 ranges, some of them have 4 ranges. So you're always looking at information. Again, Ford talks about it, but they don't give it to you till later in the year on the OEM tool. I have never seen it on a global OBDII tool, which you wouldn't, and I've never seen it on aftermarket tools so far. Now, the thing you got to understand, cells are always based on RPM and load. And they always have short-term, long-term trim readings in it, but the long-term trim is stored. That's a correction at that load, which would be a specific RPM and a specific load. If I went back to this last slide, if you saw it, I'm at a certain load on the vehicle. Notice at 27.8 and I'm at 54.5. So in other words, these are going to be based off of RPM and load. Where do we get RPM and load? Of the crankshaft sensor, and we also get load based on the MAF or the MAP sensor on the particular vehicle. So these are readings you're going to have to start looking at to do diagnosis a little bit better. Okay, your starting point in diagnosis, if you have a fuel trim related issue, is this. Air fuel related issues will always lead to fuel trim issues. So you have to keep that in mind. So will some other items on the vehicle. It doesn't matter which type of O2 sensor you're using or air fuel ratio sensor for that matter. But if you have an O2 switching style, that means that O2 sensors that go, we're all looking at 200 millivolts to 800 millivolts. Those are switching style. They can be a planar, which is basically an O2 sensor instead of a thimble style. It's going to be, inside it's going to be a flat plane that you can look at. It looks like a popsicle stick if you look at it from the distance. We also have the air fuel ratio sensor. They also can call it a broadband sensor. These also can help you with misfire problems by looking at information that comes across. So these are what we're going to start on, and we're going to check the O2 sensor first. The switching style O2 sensor should range from 200 to 800 millivolts. Some people use 100 to 900. Some of them use 800 to 175, whatever you want to use. But again, it's just switching those ranges. So I need to go above 800 and I need to go below 200. We're going to average 450 to 500 millivolts, depending on the system, the car we're working on. And the other thing, keep in mind, some of the Chrysler products now put a bias voltage on the O2 sensor. Not some of them, most of the new ones do put a bias voltage on the O2 sensor of 2.5 volts. So they're going to run 2.5 to 3.5 volts. But in the scan tool, it might give you the 1 volt reference if you're looking at that. There is also a thing called a Hertz switching rate at 2,000 RPM. If you worked on older Fords, they always told us to go up to 2,000 RPM. When I worked at Nissan, they told me to go to 2,000 RPM. So I've done it forever. you want to look at the times it switches rich to lean, and you're looking at 4 to 10 hertz. So you can put your voltmeter on it, your lab scope, and measure the hertz rating on it. You can use the lab scope to check the response time. Voltmeters do not do as good a job of that. But here's the other thing. If you've got air-fuel ratio type sensors, which is the other one we're looking at, you always want to check those for lambda, voltage, and current. Okay, so if you got a European car, they'll come up with lambda, whether it's rich or lean in that process. Some of them put out a voltage signal, some of them put out a current. So you have to look at what is appropriate for what you're looking at. I always tell everybody, don't break into that circuit. They use gold-plated connectors on it a lot of times, and that causes an issue. On a lambda sensor, one of the biggest things you want to do is make sure you check for the heater for proper response. That matches the other ones, but especially on the lambda sensors. And the other thing is check for throttle response. If I snap the throttle on an air-fuel ratio sensor, the car will start to go lean, and then it goes rich. So we have a difference. And again, make sure you understand, on an air-fuel ratio sensor, above 450 millivolts or above the 0 point is always lean, below is rich. If we have a switching toggle sensor, it's the opposite. Above the 0 point or the 450 millivolts, we're looking at a rich signal, below we're looking at a lean signal. So those are some things we can do with an O2 sensor to get started. Okay, some guidelines for fuel trim. Fuel trim can be affected by sensor output or skewed sensor output. If we have a vacuum leak, it can be affected. If we have, sometimes we have contamination somewhere, it can affect it. Good tip is always run it at idle, but also good tip is running at 2,000 RPM in the bay. Make sure that you run at 2,000 RPM and when not a real snap, hold it. Hold it for a while and let it run. Short-term fuel trim, let's talk about that. Should always track the sensor, O2 sensor output, which means is if it goes one way, it should go the opposite direction. They should always check. And it should be consistent, bank 1 to bank 2. It should be consistent, but each bank is on the particular vehicle. Now let's go over, and I've got O2 and short-term fuel trim. We'll look at those together. I showed you this before, but I want to show you how most techs you look at this. They will let go up here, and they will look at short-term fuel trim. Now I'll blow this up. You will watch this. Whenever the O2 sensor goes one way, short-term fuel trim goes the other direction. So they're tracking, which means I have fuel control. That's a big idea looking at it. Now I will make sure on most of your scan tools will not give you the average voltage. So a lot of times, that's why I'm going to tell you, you need to use your voltmeter to actually take those kind of readings. So if you look at this system, they're tracking both back and forth, looking good. I know I have fuel control in this particular vehicle. Okay, if we're looking for values, we should be under 10% for a switching O2 sensor. I like to be under 5% for an air-fuel ratio sensor because they're more accurate and they can vary the fuel a little bit better. The other thing to keep in mind, and I didn't talk about this yet, but we will now. If you're on a European car, they call it multiplicative, which means they're long-term fuel trim. So if they have long-term fuel trim or multiplicative, can be driven or changed by the post-CAT oxygen sensor. So if we have an oxygen sensor post-CAT, which means real, bank 1 sensor 1 or bank 1 sensor 2, bank sensor 2 can actually drive the fuel trim slightly on a particular car. Ford has that in their data. We hope to show you that a little bit later. So right now I'm looking at fuel trim on this particular vehicle, and if I'm looking at, I'm going to blow this up, and the top, you notice I have a fixed line of minus 4.66 on bank 1. If I go to bank 2, I'm minus 5.469, so that's there. So it means I'm slightly taking away fuel because the car's running slightly rich. And then at the bottom, I have the short-term fuel trim there, and it's showing minus 4.66, and you have the other one is minus 3.9. So I am in fuel control on this particular vehicle. Sometimes I like to put the short-term fuel trim and the long-term fuel trim on both banks, or just one bank if I can, get an idea of what's going on. Now that's one way of doing it, is graphing. Now the other way you can do this, some people do it this way. They're going to be able to look at bank 1, sensor 1, bank 2 on long-term, and short-term and short-term bank 1 and bank 2. So you're looking at information, short-term at the bottom, long-term at the top. You can do it either way you feel comfortable. I tend to graph things out here, but I wanted to show you that some people just like to see the numbers, and they will be changing as the vehicle is operating. So there's two different ways of looking at the information for field trim and the guideline on testing. OBDII, and we're looking at air-fuel ratio. It can be in current, it can be in LAMBDA, it can be in voltage, depending on the application. And if it's European, or if it's Asian, or if it's American. On this particular car, it's a Ford, I think it's about 2012, 2013. Notice I have oxygen sensor, bank 1 sensor, 1 current. Well, it's not an oxygen sensor, it's an air-fuel ratio sensor, but the scan tool will say that. How do I know that it is an air-fuel ratio sensor? Because it's in current. And if you notice, we got current. Above the 0 line, that little flat line in the middle there, that is lean. Below it is rich. So we're looking at the two systems up here, and this is a fairly good working vehicle, but notice there is a slight difference from bank to bank. There will always be slight differences because it's not always exactly the same fuel being delivered to each bank in the process. But this gives you an idea of what's going on. Again, if I snap the throttle, it should go slightly lean, it should go up and then kick down and go rich. So we're looking at good information here on this particular vehicle. Actually, this car was running well. On some scan tools in the global OBDII side, you're going to see EQ ratio or commanded EQ ratio or LAMBDA. Now, what I want you to understand, if you're looking at the data on the particular vehicle, if you're going down the road at a steady throttle, you're going to always see 1 if it's a switching style O2 sensor. If it is an air-fuel ratio, this will be constantly moving. The only time, if you have an O2 sensor that is the old switching style, the only time this will change is when you put your foot into it. If you put your foot into it for increased speed on this vehicle under a load, you're trying to accelerate, you're going to see somewhere about 0.96 or 0.95, which means is I went rich because I should, but the only time you will see this change is on a first fire up, and the minute you get in a closed loop, it will go to 1 and stay there. It will not change unless you put your foot in it. So there isn't, this time, it can cause some issues when you're doing diagnosis. So what you want to make sure is you don't use this as the only tool for you doing your diagnosis. OEM names for fuel trim. Everybody thinks when we went to OBDII everything would be the same. It isn't. When you're on the OEM side of the scan tool, you're going to look at, if I go FCA or Stellantis, they're going to call it ADAP short term, ADAP long term. They're going to use plus, or the 0 that we're used to, plus or minus 10. I'm not going to talk about the ones that be conventional on there. I'm going to talk about the exceptions. So if we look at Ford, they're going to call it short-term fuel trim. They go all the way out on it, or they will do an abbreviation SFFT or LTFT. So they're looking at, they'll abbreviate it down. So they actually put it all the way out. GM, short-term fuel trim, long-term fuel trim, no, nothing different. Then we get to start doing some cars a little bit different. Honda and Acura, AF feedback, that's your short-term fuel trim. AFFB, I call it feedback because that's what it is there, but AFFB average is long-term fuel trim. Now they're also a little bit different. They're going to follow the rules of LAMBDA that we're going to see with some other cars. So we go 1 is what they consider the center point, and we're going to do plus or minus 1. So if it's lean, it's going to be above 1. If it's rich, it's going to be under 1. So if we go up to the next one, Hyundai and Kia, field adaptation, LAMBDA sensor correction value. Well, hey, that's really neat because it explains what it's doing. It's correcting for long-term fuel trim. Again, they do plus or minus 10%. Mazda, they're going to abbreviate a little differently. Short-term fuel trim is SHRFT1, and the first time you try to find that, it'll be a little confusing, or they do long FT1. And then they do another correction based off the rear O2 sensor, and they do RO2 FT1. And again, they use plus or minus 10. Mercedes is always a little bit different. They have an idle speed adaptation, that's 1 long-term fuel. They also can have partial load adaptations. They can have up to 3 partial loads that I have seen. And so you will have 4 fuel trims on these particular vehicles. At idle speed, they're going to use conventional, plus or minus 10. When we go to partial load, they're going to go to LAMBDA, which would be, they call it LAMBDA integrator for you guys that have been around for a long time. So if we have 1 plus or minus 1, similar to what the Honda does. And if we go to Nissan Infiniti, they're going to do air fuel, our AF Alpha, that's going to be our short-term fuel trim, and a self-learn control is going to be a long-term fuel trim. Now, they're a little bit different also. So they went out and put 100, so it's going to be plus or minus 100. So if it's slightly rich, it's going to be maybe 90. If it's slightly lean, it's going to be 110. Subaru, air fuel correction 1, air fuel learning, and then those are your short-term, long-term fuel trims. Then we have an air fuel correction and learning that is off the rear O2 sensor. Now they're going to use conventional zeros we've done with everybody else. Toyota, similar, short-term fuel trim, long-term fuel trim, and then they're going to do total fuel trim, which will take in with an algorithm the rear O2 sensor input. They're going to be conventional in what they're going to do. They just make a little bit more numbers out there for you to look at. Now the older VW and Audis, they use block learn blocks or data blocks that you can look at. So you would use data block 33 for LAMBDA control, and for mixture control you would be using 32. So they're basically going to use plus or minus 10% for those also. So again, those cars have 2 long-term fuel trims, 1 for idle and 1 for off-idle. If you look at some of the other European cars, they will call it additive for idle, and they will call it multiplicative for long-term for off-idle. So I've already talked about multiplicative a little bit. So we're going to go over and look at some applications we might want to look at real carefully on using this information. But one thing I want to make sure, if you're confused by this information, go to Global OBDII. Global OBDII, everything is conventional, everything's displayed exactly the same, so you don't have to worry about remembering all this different names of everything. It makes it a little bit easier. That's what I tend to do first, and then I go over to the OEM side. Okay, we're going to be talking about feeding the catalytic converter. When I was at Chrysler Product, I used to always tell them we were going to feed it cat food. Well, the cat has to have certain food coming to it. So basically, it has to be between 0.97 and 1.03 for a good functioning catalytic converter. There are metals in there that will catalyze, they will reduce the emissions there to make it a little cleaner so it goes out the tailpipe. Not perfect, but it's a lot better than when it comes to it. Now, my next slide's talking about some LAMBDA chart. So we're just going to talk about LAMBDA air-fuel ratio. So if you look at it, or this could be on a car, this could be using equivalence ratio on a car if you've got it. So we're looking at if it's rich, it's less than 0.97. The PCM response should be negative, less than minus 10. If it says the O2 sensor is greater than 450 millivolts. Now, here's the deal. On your scan tool, it will not always give you that reference. Some scan tools will allow you to get minimum, maximum, and average. So you always start using that. One of the scan tools I got gives me a bar chart. I use that, but when I go to the graphing, it doesn't give me the information I want. This would be the correct response to a rich condition. Causes rich condition, they got some suggestions there. If we go to the next one down, we have lean, greater than 1.03. The positive is greater than 10, so we would be adding fuel to this system to correct it. And the O2 sensor voltage would be less than 450 millivolts. Now the average voltage, not the voltage there. So it should be switching above 800 and below 200, but we're going to average about 450. That would be a correct response. So if you're looking at that information, that would mean either one of these, I have fuel control. Now I'm going to take a couple here. If I'm looking at the car and I got rich or lean, 0, PCM response is 0, no fuel trim correction, and it says, O2 sensor says rich or lean, doesn't make a difference. We're in open loop or we're in limp mode. A lot of times on your scan tool, they will say open loop fault. So you want to look at some data there. Next one down, we'll just pick one of these two here. Lean greater than 1.03, and we got negative greater than -10. And it's rich, and if we look at it, if it's higher than 450, it means that we have a problem with the system. We do not have fuel control. We're not correctly doing the information we need. We're feeding information in, and we're taking the wrong response to it. And there's a couple other there that we're looking at. But the whole idea is we want the first two, and if you don't have the first two, you better start looking and see what's going on with the computer. Hopefully this is a good chart for you to use as a reference. All right, so let's go over and talk about some logical fuel trim diagnostics next. Okay, we're going to do some logical fuel trim diagnostics. We're going to have to apply some logic to when we're doing this. And the first thing you're going to have to look at is you're going to have to do a test to find when the problem exists. What load, what cell, and what RPM. Because remember, we told you that we're going to be looking at fuel trim based on RPM and load. So we look at it, you have to duplicate the problem. Don't automatically just think that you can fix something. You have to duplicate it to make sure you understand what's going on. It's always check the fuel trim and multiple cells or loads. Now, if you don't have the cells, what you're going to basically do is put an RPM up there and look at long-term fuel trim. There are scan tools out there that will allow you to run the vehicle, and it will actually give you the fuel trim in those cells for reference later on. You want to check all the possible causes, find out what's not working correctly and what is working correctly. That makes a little bit of sense. So narrow it down to what isn't working correctly. Too many people try to fix or go out and diagnose what is working or not working. So I tend to work the other way around. I tend to find out what's working correctly, eliminate those, and whatever's left over is whatever's not working correctly. You want to find and fix the incorrectly systems or sensors. Now, when you have to do this, you're probably going to have to evaluate some sensors. And the biggest one you're going to evaluate is the O2 sensor. And remember that sometimes you're going to have to use your voltmeter to actually do min, max, and average on the O2 sensor. Sometimes you want to do it at idle, and you want to do it at 2,000 RPM. Remember the Hyundai deal, it actually told us to do it at idle and 2,500 RPM. So sometimes you have to do it multiple RPM levels. You want to look at the MAF sensor per second at idle. It's going to be in grams per second. You might be looking at frequency. You might be looking at per hour, depending on the system. You want to be able to look at the grams per second on a wide open throttle, because a lot of you are doing some other tests with the system. One of the things that most technicians forget, and I used to do it too, so it's here, is the barrel sensor. And the barrel sensor is one of the key things that determine what the fuel should be at that altitude. So keep that in mind. You want to check the barrel sensor. If it's not reading correctly, you're going to have a problem with the system, and it does happen. You want to look at the map sensor at idle and the map sensor at wide open throttle if it's a speed density system. So those are some of the evaluation sensors we need to look at to go from. And then we're going to go into this a little bit more depth. A lot of you have heard of volumetric efficiency, where we're looking at the ability of the engine to breathe. And if I'm looking at this is a calculation. You can find these online. I would tell you always to make sure if you're getting one of these, make sure it has the altitude built into it. So if I'm looking at this one, it has 4.8 liters. I was at 4,205 RPM. I had MAF sensor 160 grams per second, all right? And it's gasoline. They tell you if you're looking at that. It tells you the temperature down on the lower left-hand side. Temperature at that point, and then it has a barrel reading on it. So it was 28.2 where I'm at. So I always like the ones with the barrel reading because the barrel is important. We just talked about that as far as fuel. Now, this one, when we calculated this one, I will also tell you this is usually done from a running start, rolling start, and you're going to do it before the first or second gear shift. Now, Scott Brown and I have discussed this, and we're thinking that maybe it'd be a better idea to find out when the torque of the engine is at maximum output, because a lot of cars are now torque managed engine controls. So we did this particular vehicle. So I've got 181 grams per second. Notice it said 24 pounds per minute. All right, before I said per hour, it's per minute. I made a little mistake there. The volumetric efficiency on this car is 89%. So that means this car is good. Anything above 80, I usually consider really good. Now, the problem about it is, if you're using this particular chart, it will not work on a speed density system. So you're going to use calculated load on those particular systems. And what you'd want to do is do a calculated load on it and see about 80% or better if the car's running. Sometimes 70 is okay, but mainly I would like to see 80 or better. Now, there's one other thing that I've learned from a friend of mine, Mark Warren. He used to write for some of the magazines. Mark did this one. He said at 80% volumetric efficiency, okay, 80%, if you look at the RPM, so if I went to 4,000 RPM and went to the middle here, I would be able to see what the grams per second should be. Now, I use this chart a lot faster than do the other ones because it gives me a good idea up there. So if I'm at 4,000, I got a 4.8 liter, so it's got to be between 4.5 and 5. So I should be at 5,000, we'll do 5,000. I should be between 158 and 178 grams per second. That tells me my engine is running good. This is a real neat little chart. If you can find this on there, or do a screen capture off of this when you're doing this and keep it for yourself. This is really good information to use. We want to know the ability of the engine to breathe. If we have a problem here, that would indicate we either have a mass airflow sensor problem or we have a restriction in the exhaust or restriction in the intake. Nice things to use to make sure the car is breathing correctly. Incorrect breathing car, incorrect fuel trim. We'll leave it at that. We've got a chart here from General Motors. You're going to see charts from Chrysler and other companies, but basically it's showing you the cells that you might be looking at. So you're looking at the cell number. If you look at this, there are approximately, what have we got? Approximately 6 cells up here, and 6 cells are weighted cells, which means those are the cells that would most likely have a fuel trim related code based into it. Notice number 5 has got the highest load. So you want to look at the cells as you're doing your test. The other thing is, if we're looking at European cars, they're a little bit totally different. If you look at this one, we have 3 long-term fuel trims that we're going to be looking at on a particular vehicle. So we have one at idle to just off idle, that's RCAT. This is abbreviations, I don't know what they mean. I've tried to get information on it. Then what I want to call FRAL, which is going to be somewhere about 1,400 RPM to about 5,400 RPM, but it's on a lower load. If you notice, if you look at the RPM and the loads will be lower. And then we have another one at higher load. So these are what we're going to be basing our fuel trim based off of. These are load. Now, to make this work, we have to look at the next slide over here. And the next slide tells there's 2 types of fuel control in the cars that we use up here. There's a third type that, for you racers out there, is called alpha N, where we just use the throttle position sensor and the RPM. But we have 2 types of load. We're going to use the mass airflow sensor, and we can have 2 types of mass airflow sensor. We can have the heated wire, or we can have the heated film. There are 2 different styles. They work very similar, but it's there. Mass airflow sensors can be frequency, there can be voltage. And we also have the map sensor. Now, this is the old style map sensor. Most of the new map sensors right now are built into the intake manifold. Those are the type, and we're going to go over and talk to you a little bit about what they are and what they're doing. What are the differences in this system? If you have a manifold absolute pressure sensor, it's going to measure the pressure below the throttle plate. Everybody always puts this out as vacuum. It's actually the manifold pressure under the throttle plate. One other thing you can do with this one, if you have a barrel sensor, let's say it says 28, and at idle you have 8 inches of map pressure. You subtract 8 from the 28, that tells you you have 20 inches of vacuum in the intake manifold. There's something a lot of technicians don't understand, but that tells you there. So it's a really good chart to use. Now, older cars had a Vane airflow mass sensor, and basically that was on Toyotas, Nissans. I worked at the Nissan dealership when we had all these on our Zs. And we also can have a mass air. So we're measuring the difference. Speed density is going to measure the pressure below the throttle plate. Mass airflow is going to measure the airflow before the throttle plate. So there's 2 different ways of looking at the systems. Now, if we go over and look at our mass airflow sensor, All it's going to do is basically look at the mass airflow sensor, go to a lookup table, and decide what the fuel delivery should be at that point. If I go over to speed density, it's a little bit more complicated. Chrysler still uses speed density. There are a few cars going back to speed density with the turbos and everything. So they are going to be able to measure the throttle opening. They're going to measure intake air temp sensor, the coolant temp sensor, the engine speed, the throttle opening. Basically, you're going to know where the throttle's at. And they're going to be able to determine if the EGR is flowing or not. So they're looking at things a little bit different than you would be on the other ones. It's more complicated. It takes a little bit more time. And if you ever work on a Chrysler product, there's all kinds of ways they do this. T-map, B-map, whatever. But it's good information to understand that, again, mass airflow sensor is going to measure the airflow in front of the throttle plate. MAP sensor is going to measure the intake manifold pressure after the throttle plate. That's one of the things you're going to be looking at. If you go over to the next slide, now just stop at this slide to get what we're looking at. If you look at, this is a pulse width calculation. That's how complicated it is. So you go RPM divided by max RPM, and you got MAP by barrel. And you go to throttle position times the engine coolant temp sensor times the inlet air temp sensor times sense B plus or battery positive times long-term fuel trim times the O2 times short-term, long-term, and that's how you're going to get the pulse width. This is complicated. Let the computer do it, and it's real interesting. So you can have a problem with a pulse width modulation sensor somewhere on the car. You can have a problem with the MAP sensor. You can have a problem with throttle position sensor. All would affect the fuel trim on this particular car. So let's go over and we'll talk about a few more things. Okay, we have the MAP and the MAP put up here, and they work a little different, so we're going to show you something up here. So if I'm looking at this, keep in mind, on your scan tool, up is always going to be toward pressure, vacuum will always be at the lower point on your screen. So I'm going to start this one up, and we'll see what we get up here. If we're looking at our pattern right now, when it starts, you're going to see that we have about equal up here, about 1.13 volts up there, and we're looking at information. Now, if I do a snap on this one, we'll see if we get a snap up there. There's our snap. I want to stop it right there and show you something very interesting. When you go to mass airflow sensor, it's going to go snap up, and you've got the system up there, went to 3,750. And if you look at, it goes back to 1.4, close to the throttle. But notice on the MAP sensor, you see this little spike down and then it comes back up. That's telling you that you have high vacuum in the intake manifold. So if you snap the throttle open, high pressure in the intake manifold. When you close the throttle plate, then you got high vacuum. So what happens is I increase the pressure in the intake manifold when I open my throttle. When my throttle slams shut, I should have increased vacuum in it because it was speeding up and it's going to increase vacuum. The pressure's toward the top of the intake manifold, and inside the cylinders we have the vacuum. So that's the way you're looking at it. Pressure's there. But if you look at it where it says 449 up there, that little spike down there tells you that you have good flow in this engine. If that is missing, the car is constipated or it has a restriction on the exhaust. That should recover real quickly and go back to idle. So if I come up here, I'm just going to let this thing go again. And watch what happens. It goes right back to where it should, and we have my idle readings back real close. If I don't have that little spike there, the little spike going down, that would indicate I have a restricted exhaust system on this vehicle. Real quickly you can do it. You can't do that on a mass air, but you can do it with a MAP. Just something you can look at it for diagnostics if you're looking on the car. Again, we're looking at pressure, or we're looking at airflow before the throttle plate or after the throttle plate. The MAP sensor can give you indications of pressure buildup in the intake manifold. All right, well, let's go over to a couple other things here. Okay, most technicians only use these two procedures we're going to show you for testing fuel trim. It's okay, but it doesn't always give us all the information. First of all, we're going to look at short-term fuel trim for both banks, the RPM, long-term fuel trim for both banks. We're just looking at fuel trim, all we're looking at right now. So what I'm going to do is do this, and we're going to see a video as things are going to happen. So you're looking at idle. You notice my long-term fuel trim should not be changing. We're looking at minus 2.3 on one bank and minus 1.6 on the other. And notice my min and my max at this point are basically the same. If we're looking at the short-term fuel trim, it should be going up and down, compensating for everything going on. So it's doing its job. We're at idle. The next thing we should look at is, at this point, we're going to go to about 2,000 RPM. And we're going to do this again. Remember when we first started this class, Hyundai did it at idle in 2,500 RPM, whatever you want. And again, if you look at this point, if I'm looking at it, my fuel trim has not changed. And I want to make that specifically for everybody to understand. I haven't changed pretty much the load on this vehicle. So my fuel trim at idle is pretty much the same for long term. If I had a load change, I would probably see a different reading on the long-term fuel trim. So we're looking at our data up there by 2,600 RPM. Notice my fuel trim at the top has changed a little bit. I'm going from minus 6.2 to 5.5, but I'm still averaging around 0%. So there's something to look at, but we're missing some information that might be pertinent to what we need to use. So we're going to go and show you another way of doing this. Okay, if you're going to do this particular test we're going to use to make the best use of your diagnostic time, we're going to have to develop a drive cycle test route. The first thing is you want to be able to be safe while you're doing this. You don't want to hurt anybody, you don't want to get any tickets, so your best way to do this is find a place to run it with low traffic roads if it's possible. The other thing I always tell everybody, learn to take a recording quickly. There are some scan tools that record constantly. I have one that the minute I turn it on, it records constantly. But other ones, you're going to have to learn how to turn it on quickly to do it. So find out where the real easy way to start recording. The other thing is, if needed, drive and get a partner to record the test, or vice versa. So partner drive and you record. It doesn't make a difference. Do that. You have to obey the traffic laws and traffic signs. I don't want you to come back and say, hey, I got a ticket for doing your test. No, obey all the laws. You want to set up your scan tool before the driving. Your minimum PIDs you're going to probably be using is short-term and long-term fuel trim. You can get by just using long-term fuel trim if you want to. There are some other PIDs that can really help if you want to use this, but we're going to do the chart. I have added these to it. I might want to do calculated load to make sure there's a reading there. I might want to use, if I have the ability, like on a Chrysler or General Motors, to use the fuel trim cell. That's additional up there we might look at. There is other things you can add. It's up to you to do it, but minimum you should be able to do long-term, short-term fuel trim when we're doing this test. First thing is, I'm going to add a few things up here. Step one, we're going to have a warm engine. You got to be in closed loop. I want to do idle. I do idle 1,500 and 2,500. That's what I do. You can do idle 2,500 if you want to. You want to record, at least record the short-term and long-term fuel trim. Another step I've added since I've done this is the next step I want you to do, once you get done doing that, I want you to turn around and put it in drive, because it puts a slight load on the car, and take another recording. That way you see if you have an issue, especially right off, have right off idle hesitation. It might be a good idea. Step two, go to 1,500 RPM, about 20 to 30 miles an hour. Try to do about 25 miles an hour if you can. That's low speed traffic. Record short-term, long-term fuel trim or other additional PIDs that you might want to use. That minimum short-term, long-term. Step three, go to about 2,500 RPM or do 40 to 50 miles an hour down the road, because the load will change when you do that. And again, do another recording. And it's a good idea on some of these, actually add the mile per hour, and when you go into the higher ones, that way you can come back and see what's going on, what mile per hour you were doing. It's a good idea. The other one you can do is high load, 60 to 70 miles an hour. I would probably tell you to do 60 miles an hour will work just fine. If you were on some European cars, they will not do, if you were doing a fuel trim monitor test, it would not work above 60 miles an hour. These are 4 ranges, 4 steps that you can do. That gives you a really good idea of what's going on with the vehicle as far as fuel trim. Complicated subject, but this gives you some reference material of where it happened, what's going on. You might have a car that's running great at idle, going down the road it runs terrible, or vice versa. So what you're looking at is find the time, the RPM, the load level, the vehicle speed that might be causing your issue. That's all we're doing with this particular information. We're going to do some idle testing here like every tech should do. This happens to be a Chrysler vehicle, and if we look at it, this is a recording I captured and stored back to playback. So we're doing the long-term fuel trims of 1.4 for bank 2, bank 1, the long-term fuel trim is 2.5. Our short-term fuel trim right now is minus 0.4, and the short-term on the other one is 1.6, minus 1.6. So we have this going up here. I'm going to play this. We're going to see what happens when we go live up here. It takes a while for it to get started, but it's 600 RPM. Notice our short-term fuel trim is changing back and forth. I'm in cell number 24. That's what we should be in. Notice if we look into data, the long-term fuel trim is not changing at all. All of a sudden, I went up to about 500 RPM as we switched over to cell 4. Notice again, it's a little bit different on my long-term adaptive. It changed a little bit. Notice the top one, it went from 1 something to minus 0.2%. So I was in a different cell because I'm at 4. That's why I tell everybody it's a really good idea when you're doing this kind of testing to test it at idle 1500, and we're going to do 2500 or a little bit higher on our next slide. So I'm going over to my next slide, and we're at 2500 RPM. I've added something in here. I've added, if you notice, I got vehicle speed, and because I'm getting ready to go do a test. I probably should have had it there before, but now I make sure it's there. I can add that as I go across. I'm in my current adaptive cell right now of 2. I'm going to start this vehicle, this recording, and it went to cell number 3 real quickly. And if you notice the long-term adaptive, when I'm graphing this out, you notice that I have some changes in long-term adaptive. Why do I have changes? Because I am changing speed. I went up to, right now I'm at 2700. I went up to 2800 RPM. And if you notice, I went from negative 9.8 to 1.4 on the left-hand side over on bank 2. That was a long-term fuel trim. The reason it changed is because I changed my cells. If I go over, there's my RPM, long-term adapt on 1, I went from minus 8.4 to 2.5. Still within reason, we can do it. Now, here's what you're going to have a little problem with. I only went from cell 2 to cell 3, back and forth a couple of times. So it's not going to be a drastic change on the bottom of this, but if you see, there are some changes on the, when you go to current adaptive cell, you're going to see a little square wave looking pattern as it's changed cells 2 to 3 going across. It went from 24 when you started. Right now it's in cell number 3, but we did start in cell number 2. So you're looking at the adaptation based off on cell and base, and when we're doing that, we're also basing it off of load on the engine as it's changed RPM. We're going to go do some more testing here. Okay, we're going to look at what you would do at 20 to 40 miles an hour. I've got long-term adaptive on both banks. I have short-term adaptive on both banks. Notice I added vehicle speed in, or I have speed up here to make sure that it's there, and I'm at about 19.5 mile per hour, and I have the current adaptive cell at cell number 10. If I set this up, and there's a recording that I would do as this drive cycle, so we're looking at it. Notice it went to cell number 9 immediately as we're going up here. As I change in RPM, things are looking. So if I'm looking at them at 27, almost I want to look at 30 miles an hour if I possibly can. And all of a sudden at 30 miles an hour, 32 miles an hour, I went to cell number 0. I changed. Again, this is giving you a reference when the problem is. So if I was driving the car to correct the problem, I would want to drive it and bring myself in that cell. By looking at the RPM and a couple other things up there, I can get an idea of what I need to look at. So this particular vehicle, when he went to cell there, his long-term adaptive was minus 2.3, short-term is minus 9, so apparently his car running slightly rich at this point. And if you look at engine RPM, it's like 1213, vehicle speeds 22 or 32.5, long-term is 2.1, and short-term adaptive is 4.1. Now, the reason I'm using it this way, let's just clarify it. If I tried to put everything on the, depending on your scan tool, I might not be able to graph all this information, and it gets small. So I usually use this and see if I can go back and open it up with a graph later. Some scan tools, you know how to do it. Other scan tools, Whatever's on the screen is recorded. Whatever's not on the screen is not recorded. That's why we do some of these changes and going across, and you'll see that as we go on. Okay, you can see I made a mistake on this one. I want to make sure everybody realizes that. I have the long-term adaptive on bank 1. I didn't do bank 2 on this particular vehicle. Sometimes you will make a mistake there. I'm looking at engine speed and vehicle speed, and I'm looking at my current adaptive cell. Before it was 10 and 9, now we're at 14. So I'm just going to go ahead and click OK on this one and go across. I want to try to get around 50 miles an hour again in the middle. On my current adaptive cell right now, it's changing as I'm doing load. It went to 13. And if you look at it right now, I'm changing as I'm trying to drive this vehicle at this range. I am changing cells. Notice I'm going constantly changing cells at the bottom because I'm trying to maintain it. The whole trick of this is you want a steady throttle. This is a mistake. This should be redone. That's why I'm telling you this. So I'm looking at my long-term adaptive -2 to 4.3. Short-term, it is -7 to 13.3. Do I possibly have at this RPM range a fuel trim issue? Yes. But I think part of the problem is on this particular stuff, I didn't maintain a steady throttle. So that's something else you should be looking at. Some of you will go out and pick a TPS sensor in addition to this. It's not a problem. It does help sometimes. So I would have to redo this test, look at the throttle, and make sure it maintain a steady throttle to get this test correct. Okay, right now we're at 59 miles an hour. What I'm going to do is go ahead and start playing the video. And if we look at it, it takes a little while to get started. We did 56, 58, and we want to try to get it above 60. So right now we hit 61, 62 on it. Notice I'm in cell 15 this time. Notice my long-term fuel trim is 1.4 and it's changing. I'm changing cells. Again, this is very hard sometimes to do this because you want to maintain a steady throttle. So if you look at it, I'm really close to 1700 RPM steady throttle, and I'm looking at my readings again. I'm going to be changing cells depending on the load on the vehicle as it goes across. So that's something you're going to run into, and it's not a big problem. But again, try to do this as best you can with a steady throttle and look at the cells. And if you don't have the cells, what did they tell you to do? Look at calculated load. Now I'm going to go over to one more slide here in just a second, and we're going to look at possible causes. So this is something we remind each other. We talked here with Sam and I talked this over. If long-term both banks are out of range, you have some kind of input sensor that affects the car. So that could be your MAF, your barrel, coolant temp, air temp. It can be a fuel system problem, pressure or volume. It can be breathing problems, the catalytic converter. If you have one cat, can be stopped affecting both. If you have long-term fuel trim uneven between banks, you could have a specific cylinder problem. You can have an injector ignition mechanical problem, vacuum leak on one bank. You can have a bad O2 sensor on one bank and a good one on the other. You can have a misfire on one bank. There is a new code that comes out. It's called a P219A or 219B. That is a fuel trim imbalance per cylinder. So those are other ones you want to start looking at. So we've got this information. I want to thank you for watching. Make sure you check the other YouTube videos we have here. You can also check us out on social media. And we always thank you for attending, and we'll see you next time.